Hi everybody, I'm John Swanson from Synopsys, coming at you from the 59th DAC here in San Francisco. Today I'm going to talk about latency in high performance computing applications. So as everybody I'm sure is aware, there's many new applications coming out from the HPC data centers, which is an area that I really focus on, through automotive, mobile, the healthcare, memory, just so many different applications with latency requirements that it's really important to understand what latency is, how it's calculated, and what it will mean to the end product. Everything is smart. It seems like, no matter what we're talking about, we want it to be smart. One of my favorite examples is the pet door. So you may have seen, it's online, you can Google the smart pet door, and he was developed by an Amazon engineer who didn't want his cat bringing dead mice and dead birds in the house. So he built a little AI on the cat door, and it uses the video and says, hey, you can't come in, you've got a bird in your mouth, and it won't open the door. From that to the smart everything which is out there, just constant training. This innovation is really being driven by the semiconductor industry and the merge of the hardware and software, kind of the smart everything, the SysMore era. And it's by big data, massive compute, and machine learning are driving all of this. So let's look at what latency really is. Now, when people talk to you about latency, they'll say, oh, my latency is X. It's important to understand what they mean by X, because the numbers can vary. So fundamentally, it's the time it takes to go from A to B and then back to A. Not just one way, we have to do the round trip to calculate latency. If you think of high performance computing, there's sort of two main areas. There's PCI Express, CXL, which is inside the box. So if we're doing lots of memory accesses and things like that, we're going through these interfaces, and die-to-die as well. When you go outside the box, it's Ethernet connecting the bots together. So again, a source of latency. If your memory is in a separate box in the data center from your compute, then you're going out through an Ethernet cable, most likely, to get data. So the distances and the number of boxes can definitely impact latency. So when we think about it, there are many sources. There's the network. What is the transport media? Is it optical? Is it cable? There's the storage. There's the actual compute infrastructure. But probably most important is the actual application. And the reason I say this is you think of people that play games on PCs. I recently bought a new keyboard and mouse, and I was surprised that you could get these extremely low latency mice for people that do gaming. And I'm like, why would you spend $200 for a mouse? And so, oh, for the gamers, it's so important to latency. Well, this is an example of latency in an application. If you're in an automotive application, and an auto car today is effectively an HPC platform on wheels, latency is the time it takes to maybe stop the car. And so there's different requirements depending on what we're doing. All of these things impact it, and where we can make the biggest impact is in the semiconductor hardware that drives all of this. Now, latency is complicated, and it's important to understand this. If somebody says, my latency is X, you need to get more detail. How is it set up? What is the transmission media? How are the packets? If you measured latency with jumbo packets, it's probably going to be better than if we have a bunch of fragmented packets. Do we have to do lots of disassembly and reassembly? How many lanes are there? What speed are you running? Is it a 10 gig network? Is it an 800 gig network? The interface widths, error correction, security, bandwidth, tons of things and factors actually impact the real latency. So it's important to understand the system that you're targeting and what the latency requirements of the hardware are actually going to be. Calculating it is actually very simple. You have a TX latency, and in Ethernet, which is what this diagram is set up for a max and PCS, your RX latency is where you have the biggest hit, because we have a Reed-Solomon FEC at the high speeds, and it is the bottleneck that we're constantly working on improving. It's the biggest hit in latency. So we go up through the RX, down through the TX, and what you can see is the total latency is these two plus the application time. So if I'm doing anything in the application, my latency is going to be higher than if I'm just shoving the data through it, for example. Now, when we think about Ethernet, there's different things you can do to control latency. 802.1.q, very common in data centers. I could give high-paying customers more priority, everything gets through at a predictable time, nothing gets lost. From that, we developed audio-video bridging, which was kind of the beginning of the whole TSN standards. Audio-video bridging gives us traffic shaping, the ability to have a certain number of channels that we can control the latency on. It's very good to make sure everything gets through, but it was really not set up for control systems. And when AVB started coming out, the automotive engineers started looking at it and saying, hey, we could use this too. And this is where time-sensitive networking came out. Time-sensitive networking gives us very precise control of the latency in an application, makes it very predictable, but it can be a bit complicated to use. Not that bad, but it's a learning curve because it's a whole bunch of tools that you need to use to get this done. So what can you do to manage latency inside the chips? The first thing is write the RTL for the best synthesis results. And this is something we know a fair amount about at Synopsys, and we actually published coding guidelines for data path synthesis that will help engineers learn how to code better data. Look for the largest block. I've seen many designs that are over-constrained. People put very tight constraints on their block. It's really not what we want. Let the synthesis tool do optimization, eliminate the gates, improve the latency. Synthesize in time and context. Again, bring your timing out as far as you can. Let the engines optimize. Consider the library you're using. Some libraries are very fast, some are not so fast. And use complex functions when you can, because they can help optimize it. All of this is incredibly documented in the data path coding guidelines, which are available on the Synopsys SolveNet site for anybody to use. Now, we apply all that to our interface IP portfolio. And if you think of latency in applications, whether it's a mouse or an HPC data center, there's different components: PCI Express, USB, DDR, SATA, Ethernet, Bluetooth. All of these different interfaces impact the total user experience and the latency. So remember, everybody says we want latency to be as fast as possible, but that's not always the truth. I mean, latency means the human being needs to have a good experience enjoying his application. So let me kind of close by simply saying, new applications are driving new standards for deterministic latency. Yes, we want to make everything happen as fast as possible, but the most important thing is making sure that the latency matches the user's experience. The requirements depend varying on the application. There's many different things that impact it. Make sure you know what environment you're going into so you can calculate what the real latency will be. HPC and data centers are driving latency to extremes, and it's not just in the hardware, it's actually in the way the data centers are getting built. So for example, if the memory is located in a separate rack from the compute, we have to go back and forth. If we can co-locate these things or even include them in the same box, we can reduce the overall latency. So at Synopsys, we offer a variety of interface IP solutions, many of them architected from the ground up for low latency, and we work with our customers to develop their best products possible. So with that, I'd like to wrap up and say thank you very much.